this is recording. Okay, good. So the starting point of all classical physics is the action principle. You write an action, you write Lagrangian, and we discussed last time that the principle of least action, which is this, is equivalent to the Lagrange's equations of motion. And here we assume that this is some x dot, some position of some particle or some other degree of freedom, giving me this equation. And this is for one degree of freedom, one particle or one oscillator or one thing. So degree of freedom is the thing that changes, that is your variable, you know whatever it is. And you get one. But suppose you have many degrees of freedom, then I can write it as an index I, where I takes values 1, 2, 3. And then for each I, meaning for each of the particles or each of the degrees of freedom, I will get one equation of motion. Okay. So for example, if I have two harmonic oscillators, my Lagrangian will look like this: half mx1 dot square plus half mx dot square minus half kx1 square minus half kx2 square. Okay. So here they are, which I can write in this form as I half mx I dot square minus half kxi square, where I takes values from 1 to 2. Okay, these two harmonic oscillators. And if I have this two oscillators, I could have n oscillators, and then I would write this as in the same form: I is equal to 1 to n half mx I dot square minus half kxi square. And then these are just uncoupled oscillators. Then if I plug in the Lagrange's equation for each value of I will get the same equation of motion basically, which is half mx I double dot plus kxi equals 0. Okay. So this is just to say that I am using this I as a label for the degrees of freedom. The degrees of freedom meaning, again, the thing that changes, the variable that we have in our theory, the thing that we observe to change, that is what we call the degree of freedom. And the things that label it are called parameters of the theory. So I is a label. I is labeling which oscillator I am talking about. What is the function of I in this? It is labeling for me which oscillator am I talking about. I have many oscillators like in this picture, and this I is a label of which oscillator I am talking about. Okay. So in this theory, so for example, so now what is a field? So to understand a field, first let's consider the same picture of many harmonic oscillators, and suppose they are all in the y direction, and they are placed along the x direction, as this is the first oscillator, second, third, fourth, and so on, many oscillators, n oscillators placed at some maybe constant distance or whatever, and they are oscillating along the y direction. And so this is, and so this I call y1, y2, y3, y4, and so on. And so this I, which is 1, 2, 3, 4, is the label that is telling me which harmonic oscillator I am talking about. And then I am looking at all these different harmonic oscillators. Okay. And this is a system with finite number of degrees of freedom. Each oscillator represents a degree of freedom. Now suppose I have, instead of finite number of oscillators, I have one continuous string, like a guitar string or any string, which I can pluck. Then all of it will move. And then at each point I have 1 degree of freedom, because this point could be somewhere along the y, this point could be somewhere. I mean, all of these points I have to separate. If I want to specify the whole string, how the string is, I have to specify the displacement of each point on the string. The string can look like this, or it could have looked like this, something after I have plucked it. So to specify the whole string, I have to specify the displacement at each point. And then what is the label that I can use here? So if I have y at each point is my degree of freedom, here I was using I to talk about which harmonic oscillator. Now I have to say the displacement at which point. So I should write y of x, because x is the thing that specifies my point, which point I am talking about, whose displacement I am talking about. Am I talking about the displacement at this point? Then this is the value of x. Let's say x is equal to 5. If I am talking about this point, maybe at x is equal to 2. So that when I say which point, it specifies the displacement of each. And when I give this data for all x, then I have specified the state, the displacement at each point. So going from many particles or many degrees of freedom to fields, and this is what we call the field, as we discussed earlier, that when I have something that is a continuous system, has infinitely many degrees of freedom, that is what is called a field. So finitely many particles to fields is the label changes from I, which is a discrete label 1, 2, 3, 4, to a continuous label x. So this is discrete and this is continuous. Okay. So I can think of other fields. For example, temperature is a field. I mean, at each point there is some temperature. Or you could say air density. At each point there is some density of air. All of these also will vary with x. So I have x, let's say in 1 dimension, or usually in 3 dimensions, x, y, z. I cannot draw in this paper. Let's say 2 dimensions I draw x, y. And there will be some temperature gradient, something. At each point there is some txy. So at this point there is some value.
When you're representing it as a field, we wanted to give a continuous notation, right?
Yes.
A complete expression which represents it.
Yes. Okay. So the way to do it is using a function of x and y. So at each space point there is a function which is takes some value. What are some other examples of fields? Let's say for simplicity, similarly electric potential. You could say electric potential, and that also can take different values or some in xy direction, take different values. Usually we talk about electric field and magnetic field. Of course, it's difficult to draw in paper because those are vector fields. So electric field, let's say x, y, z. These are also fields. I cannot draw them, but in a simplified picture, I might draw something like x, y in 2 dimensions, and at each point there is a vector, and that would be a way to represent the electric field. The point is simply here that x, y, z, these guys are now labels of the field. They act as labels. Okay. So what is the degree of freedom here? The degree of freedom is the value of the electric field at each point. The thing that is changing, the thing that we are tracking, is the value of the field at each point. So when I'm going from, so the point that I want to make here is that when we study mechanics, what we study is, in mechanics, our degrees of freedom are the positions of the particles. And then these we label as some x, I, because these are positions. But in field theory, when I talk about x, in field theory, it will be some f, some field, let me call it some, I don't know, t of x. So the role of the label is now taken by x. X is no longer my degree of freedom. I am not observing x. X is not the thing that is changing. X is simply labeling the point at which we are measuring the field, at which the field is changing. It is playing the same role as I. Here I was specifying which harmonic oscillator I am talking about. I is equal to 4 is this oscillator. Similarly here x is equal to 3 is this point where I am looking at the value of the field, value of the displacement. So there is a change of status for x. Space is now, x is now a label. It is no longer the variable in mechanics. So this should not be a confusion. This is the thing that changes. This is the label. Just like this was the I was the label, and these are the degrees of freedom. These are the variables.
So each label is a degree of freedom. That's what
No, label and degree of freedom, two different things. The degree of freedom or the variable is the value that changes, and the label is the one that is telling you that which variable I am talking about. So if I have 5 harmonic oscillators, what will I observe? I will observe the physically the thing that is changing, the one that is given in the Lagrangian or the equations of motion. The equation of motion is about the displacement of the harmonic oscillator. So when I solve the equation of motion, I solve for the displacement of harmonic oscillator. I don't solve for I don't solve for which harmonic oscillator I am talking about. That is just me marking which harmonic oscillator I am talking about. So first I mark it and then I solve the equation of motion. Similarly, if I have field, I want to solve for the field. I want to solve for say temperature or electric field or magnetic field. The label is the one that tells me at which point I want to solve. I want to solve the electric field here, then x is something. Say this is the origin, so x is 0, and I solve the electric field here. The electric field is the one that I will solve using the equation of motion, that is the variable, and the x is the label. Okay, so is this point clear? Okay, so the reason I make this point is now there is a change of status for the symbol x. It is a symbol for something that is labeling the field. It is now a parameter. It is not a variable, it is a parameter, meaning I am not solving for x in the equation of motion. So this is degree of freedom or variable. This is the thing that changes with time, or the thing that we solve for in equations of motion, that we solve for using equation of motion. So in the Lagrangian, I had Lagrangians of x dot, right? This was the variable. So if I have now Lagrangian for or write the action for the some field, then this will look like what it should look like. So let's say I have a field T of x, then what do you expect this to look like? Would be Lagrangian of T of x and maybe derivatives of T of x, okay, and derivatives. Okay, so let's see an example of this to make this explicit. Okay, so to go back to the example that we had done earlier, which is the string, the non-relativistic string. So let's recap the non-relativistic string a little bit. So we have some kind of a plucked string, some string system, some could be again, could represent some string that we just pluck, and then we want to find the equations of motion. So the forces acting on it are the tension of the string. That is the only force here. We are not ignoring gravity, just a string in vacuum. So if I take, so this is some string that is here, and I am taking some infinitesimal portion of the string. So this black line is some infinitesimal portion of the string. So it looks like this. So there is a force of tension acting along the left, along the right, and we want to find the net force. So this is some infinitesimal portion, some dx, okay, dx, and so this point is at some point x, this point is at some point x plus dx, this is t. We are considering only the vertical motion here, and so the angle with the angle theta, the vertical force is t sine theta, which you can show is for small angles is t dy dx. The details are not so important. So the force at this point is t dy dx at x plus dx, and the force at this point is minus t dy dx. This is also t dy dx, but this is at the point x and this is at the point x plus dx, and the net force is the difference between the two, which we saw in the last class was d2y dx2 into dx, and mass, if the density, that is mass per unit length of the string, density is rho, then mass of this infinitesimal length is rho dx, and acceleration is d2y dt2. So equation of motion is rho dx, mass into acceleration d2y dt2 equals t d2y. So I should write as partial derivatives, because y is a function of both t and x. It changes with time and it varies with which point we are talking about. So I should write partial derivatives del 2y del x2 equals t dx del 2y. So this is my bad. Dx del 2y del x2, which gives me del 2y del t2 equals t by rho del 2y del x2 by cancelling the dx on both sides. Okay, so this was what we had done last time. This is the equation of motion. Now we want to derive the Lagrangian for this, and we will derive the Lagrangian in the old fashioned way, which is kinetic energy minus potential energy. So let's first of all write down the kinetic energy. This part is easy, mass into velocity square. I've already written it down for you. Mass velocity square into half mv square. Okay. Potential energy we have to find. So we will find using this formula what is the work done, and the work done is the potential that is stored. So that is given by Fty is equal to dW. F is force, which we have found to be T d2y del 2y del x2 into dy, because we are displacing by some y, and then this you can write as t del 2y del x2 del y del x into dx, or dy dx into dx dw, and this you can check is actually d of half t del y del x whole square is equal to tw. Why? Because if I take d inside, I will get d of half t goes outside, dy dx square. So this is d is d dx of dy dx square into dx, because if dx cancel, I get this again, and if you take this derivative, you will get half 2 comes down dy dx, and then chain rule d2y dx2, which is the same thing that we had here. Okay, so this is correct. So the kinetic energy is potential energy is half t dy dx whole square, and the Lagrangian. So this is for a infinitesimal length. This is the kinetic and potential energy for an infinitesimal length. Sorry, there's a dx over here. Oh, my bad. There's a dx over here. Infinitesimal length. And then for a full length, I have to integrate over all the full length of the string, and that gives me this. So I have this kinetic energy, which was rho del y dy dt whole square half minus t dy dx square integrated over length. So now the action, which was the integral of the Lagrangian over time, looks like rho. Actually, let me for simplicity just put rho is equal to 1, t is equal to 1. Just consider a case. And this is, then I can write as, this is y dot square minus y prime square, where y dot is dy dt and y prime is dy dx. Just simplifying the notation a little bit, and there's a half outside. So this is the action. Now what is interesting about this action is that there is a kind of symmetry or the status of space and time are the same here. You see there is an integral over dx dt, dx and dt. Both are being integrated in the total action, and there is a derivative with respect to time appearing and a derivative with respect to space also appearing. And what happened was, this happened because space or x is now no longer a variable. It is also a label. It is also a parameter of the theory, just like time was. Time was also not a variable. We were not solving the equation of motion for time. We were given the time, and then we were saying what is the position of the particle at this time. And similarly, now we are saying what is the value of the field at this time and at this position. So both things are now labels. So time and place, time and space have same status in field theory.
So you're
Yes.
kind of, in order to find the entire action, you are integrating it over the entire space and time.
Yeah, so Lagrangian, to find the Lagrangian, I am integrating over all space. And the definition of action was, going back here, integral over the Lagrangian. So I forgot to write a t here, dt. So it is integral over Lagrangian over time. And then I just substitute here, in, dt, and I get this. And so now it makes sense, because the integral is over the Lagrangian. It makes sense to call this guy something, this part which I am integrating over, and that we give this a name. We call it Lagrangian density. So we write L is equal to dx into this kind of curly L, which is Lagrangian density. This is called the Lagrangian density. This is the Lagrangian. So whenever I write a curly L, that will mean a Lagrangian density. And then the action is, in general, this will be not just dx, but it will be integral over all space, d3x, Lagrangian density. And the action will be integral of d3x dt, Lagrangian density. And d3x dt is volume of not just space, but space-time. So we might write this as d4x Lagrangian, where d4x means d3x dt, which means volume element of space-time. So there's a nice symmetry between space and time kind of emerging when we just simply write things in the language of classical field theory, language of field theory. And this will be important when we actually study relativistic field theories, because we want to treat space and time in the same footing, because that is the lesson of relativity, that space and time are very, very not so different. There is one entity called space-time. So our arena of all physics should be space-time, not just space and time. And therefore, in this language, it is kind of intuitive that that is happening.
So here you took it as Lagrangian density.
Yes.
Then instead of dx, you're taking it as d3x.
Yeah, so I'm saying in general, this I'm studying a one-dimensional string system. It has one dimension. So I have just integration over x. If I studied an electric field or magnetic field, which can take different values at each point, then I would get naturally three dimensions. So the integral will also be over 3 dimensions. And the Lagrangian will be also function of x, y, z and the derivatives.
Because we're assuming it to be 3, so we are taking it as 3.
I mean, we have 3 dimensions in space. So what is the most general case? The most general possible case is 3 dimensions, right? So yeah. Okay. Now we have to say what are the equations of motion when I have. So okay. So now we see that the Lagrangians are indeed function of have a form like this that we originally discussed. What will Lagrangian look like? We said that it will be a function. Lagrangian will be a function of the fields and their derivatives. And in this case, it was only the derivatives. The field did not appear, but it was a function of the derivatives of the fields, time derivative and space derivative of the field. So generally, the Lagrangian will, or the action will be L. So for some field t, it will be a function of t, x, and by x I mean all of the derivatives, x mu, and all its derivatives with respect to space and time. So del x mu, del tau, right? These are, we know the velocity. Sorry, my bad. So it will be a function of t del x and all the derivatives of t. So del x mu of t. Okay. This means all the derivatives. x0 is derivative with time, x1, x2, x3. All the derivatives. Okay, so this is the kind of form that the Lagrangian will take in general. And then how will the Lagrange's equation of motions look like when we have this kind of complicated Lagrangian? We will not derive this, I will just tell you the answer. But before that, this is a little bit complicated to derive. Why? Because now we are dealing with, not with functions, but with functions of functions. And these are called functionals. Function of function. So a function is something that takes some number and maps it to some other number. A functional is something that takes a function and maps it to some number. Okay, so this is called a functional. So here the action of the Lagrangian is a functional because it takes because the Lagrangian, it takes some function t of x, let's say a field, or y of x, and its derivative also, and it maps it to some number which is given by this. When you do the integral, I will finally get some number. And so this takes functions, two functions in this case, y dot x, or y prime x, y dot x, and maps it to some number. Because when I do the integration, I will get some number. Okay, and so now to find the solve the del s is equal to 0, we have to do variational calculus with functional derivatives. We have to use, so this I am just saying for general knowledge, we have to use not ordinary derivatives, but we have to take derivatives of functionals, not just functions. So these are called functional derivatives, which we will skip. The topic we will skip unless one of you wants to learn it, then we can discuss. And so then we get some other result. Then we get the result we do, which I will just write down, the Lagrange's equation of motion of fields.
So isn't it just chain of derivatives?
No, because now you are taking a derivative of a function null with a function. It's a chain of derivatives, but it has its own rules. So you cannot, so you are taking some function of f of dx, and the question is, how do you take a derivative with some other function which is f of x? So that has some definition, and which we will not go into. And so the final answer is, so if we were taking with only one variable, it would be chain of derivatives, but we are not taking derivative with one variable, we are taking derivative also with a function. Okay, so the final thing, the Lagrange's equation of motion is given by, so suppose I have a Lagrangian density, this is the Lagrange density, remember, of some function t of x, and then all the derivatives, let's say for simplicity, there are two of them, then the equation of motion looks like del L. So the usual equation of motion for was d dt del L del x dot. This was for mechanics. Just for comparison, I'm writing this minus dx was 0. And in this case, the main thing that changes is now I have space and time on the same footing, right? Space and time at both levels. So I will have del L del t dot, this guy, del t, and I will also have minus del L del t equals 0. So far it looks the same, exactly the same as this, but the one thing that will change is now I also have t prime and the derivative with respect to space, and it will have the same status. So I will have del x del L del t prime also here. Okay, so this is the new addition, kind of a new addition, which is space and time come on the same footing when I am doing this. And remember, the other difference is that this is the Lagrangian, whereas this is the Lagrangian density. And so in more general notation, where we use the 4-vector notation, we write this as del L. This is a derivative with respect to the derivative of the field. So we write it as del t del of del or del, sometimes we use this notation of del, and this is del t del x mu. Most generally this x mu, and this is del of del x mu. Okay, repeated index meaning there is a sum. This means nothing but del x naught del L del t del x naught plus del x1, same thing, del t del x1 plus dot 2 3, which is exactly the same term that I have written here, minus del L del t equals 0. Okay, so let us use this newfound knowledge on the Lagrangian that we wrote down for the string. So Lagrangian for the string, Lagrangian density for the string was quite simple, y dot square minus y prime square. So let's see, we have the equation del L del y dot ddt minus ddx plus ddx del L del y prime minus del L del y equals 0. This is the equation of motion. Now out of this there is no y appearing in this, so this is 0 because there's no y in the Lagrangian, and I have only these two terms. So I have ddt of del L del y dot is 2y dot plus dtx of, there's a minus sign, plus this is 2y prime, and so I get 2y double dot minus 2y double prime is equal to 0, which is nothing but del 2y del t2 equals d2y dx2, which is the equation we had when we restore t and rho.
Yes.
So this is the correct Lagrange's equation of motion. I have not been, lying to you that this is the equation of motion, and this is how we get this. So this is what we will do, and let me stop by giving one example of a field theory that we will study in the upcoming classes. Actual example, scalar field Lagrangian. So the starting point of again any scalar field is Lagrangian, and in 4 dimensions. This is del phi del t square minus grad phi square plus m square phi square. This is called the scalar field Lagrangian, and here the Lagrange's equation of motion is del phi del t square grad phi square plus m square phi square, and this is the mass of the field. So I'm just we will study this particular example for most of our course. We will study this scalar field theory. This is an example of a field theory. Physically there is no such field, except there are no scalar fields in nature except the Higgs field. The Higgs boson that you may have heard of is given by a scalar field, and this is the kind of that has a more complicated Lagrangian. This is a simpler example, and this is the simplest possible field that one can write, which is relativistic. So this is an example of a relativistic field. This is a relativistic field, and this is the mass of the field. And if we derive, let's consider the simple case where the mass is 0 and I have just one dimension, and then the Lagrangian reduces to something that you will feel familiar with, because it is also exactly like the Lagrangian of the string. So it looks like the Lagrangian of the string. So this is not, although this might look a little bit more complicated, this field is also not very complicated. It is something just a little bit more general than the non-relativistic string, but we will study this and we will see, we will develop the tools of quantum field theory using this. Okay, so I will stop here for today. If you have any questions, go ahead and ask. Otherwise,